Time is not what you think it is right now. As you watch this video, time is passing differently for you than it is for someone on a plane flying overhead. And no, that's not a metaphor. That's not poetry. That is a measurable, verified, scientifically confirmed fact about the universe we live in. The clock on a GPS satellite actually ticks faster than your watch. Engineers have to correct for this every single day, or your navigation app would be off by miles within hours. Everything you've ever experienced about time, the steady, reliable 1 second per second march of minutes into hours into days, is an illusion, a very convincing one, but an illusion nonetheless. Time is not fixed. Time is not absolute. Time is not something the universe keeps track of from some central cosmic clock. Time bends. It stretches. It slows down. And depending on where you are and how fast you're moving, your time and my time are simply not the same time. That is the reality Einstein handed us in 1905. And most people heard about it in school, nodded, said, "That's interesting," and went back to assuming time works the way it always seemed to. Today, we're not doing that. Today, we're actually going to understand it. Not just know it, understand it. Feel it in your gut the way Feynman always insisted you should feel physics. Because here's the thing, once you truly grasp what Einstein was saying, once you see why time must be relative and not just accept that it is, you will never look at your watch the same way again. You will never think about a distant star the same way again. The universe will genuinely look different to you. And that's not an exaggeration. That's the promise of physics done right. So let's start at the beginning. Not Einstein's beginning, an even simpler beginning. Let's start with light. Light is strange. Magnificently, unsettlingly, beautifully strange. And everything about time dilation comes down to one jaw-dropping property of light that took humanity thousands of years to discover, and that still makes physicists grin when they think about it. Light always travels at the same speed. Not almost the same speed. Not roughly the same. Exactly the same. Always. No matter what. Now, that might sound reasonable until you really think about it. Because in ordinary life, speeds add. If you're on a train going 60 miles per hour and you throw a ball forward at 10 miles per hour, someone standing beside the tracks sees that ball moving at 70 miles per hour. Speeds combine. That's just how things work, right? Not for light. Imagine you're on a spacecraft traveling at half the speed of light, which is already an almost incomprehensible velocity, about 93,000 miles every single second. Now you turn on a flashlight and shine it forward. How fast does that beam of light move away from your spacecraft? You might say, well, it should be the speed of light plus half the speed of light, so 1.5 times light speed. That's just common sense. But the universe doesn't care about common sense. The beam moves away from your spacecraft at exactly the speed of light, not faster. And here's the part that makes your brain want to protest. Someone standing still, watching from outside, also sees that beam moving at exactly the speed of light. The same beam. The same light. Two observers. Different velocities relative to each other, and yet both measure that light traveling at exactly the same speed. How is that possible? Stop. Think about that for a moment. Because that's not just a quirky factoid. That is the entire architecture of relativity sitting right there. And once you feel the weight of what that means, everything about time dilation becomes not just believable, but inevitable. If both observers, the one moving and the one standing still, must measure light at the same speed, something else has to give. Something has to adjust. Something in the fabric of reality has to flex and bend so that this constant speed of light is preserved for everyone. That something is time. Here's where Feynman would pull out his favorite tool, a thought experiment. And it's a beautiful one. It's called the light clock. Imagine a clock, but instead of gears and springs, this clock works by bouncing a single photon, a particle of light, back and forth between two mirrors. Every time the photon completes one round trip, that's one tick. Simple, elegant, and more importantly, it uses light, which means its behavior is locked to the laws that govern light itself. Now imagine you're holding this light clock while standing still. The photon bounces straight up, hits the top mirror, bounces straight down, hits the bottom mirror. Tick. Up, down, tick. It's traveling the same distance every tick. You'd measure its frequency, its ticking rate, as perfectly steady. Now imagine a friend watches you walk past with that clock at a very high speed. From their perspective, you and the clock are moving horizontally while the photon bounces vertically, which means from their point of view, the photon isn't traveling straight up and down. It's traveling diagonally, up and forward, then down and forward, tracing a zigzag path through space. But here's the critical constraint. That photon still has to travel at the speed of light. It cannot go faster. So if the path it travels is longer, if each diagonal stroke covers more distance than a straight vertical stroke, and the speed is fixed, then each tick must take more time. Your friend, watching from outside, sees your clock ticking slower than their clock, not because anything is broken, not because of some trick or interference, but because the geometry of the photon's path is different from their perspective and the speed of light is non-negotiable. Time itself, the ticking of every physical process, slows down for moving objects. This is time dilation, and it's not a hypothesis. It's not an approximation. It's been measured directly, repeatedly, with atomic clocks on aircraft, with particles in accelerators, with GPS satellites orbiting the Earth. The universe does this. It actually does this. And here's where it gets interesting. The light clock isn't a special clock. Any clock, mechanical, biological, atomic, will tick at the same rate as the light clock. Because if they didn't, you could compare them and figure out your absolute velocity. And Einstein's relativity forbids absolute velocity. So everything slows together. Your heartbeat, your aging, your thoughts. Every physical process in your body runs slower when you're moving fast relative to someone else. Now, you might be thinking, okay, but we move all the time. We drive cars, we fly on planes, we spin around on a planet that orbits a star. Why don't we notice? Because the effect only becomes significant when you're moving at an appreciable fraction of the speed of light. And light moves at 186,000 miles per second. A commercial airplane moves at about 600 miles per hour. That's roughly 1/10,000,000th of light speed. At that velocity, time dilation exists. It's real. It's measurable with precise atomic clocks. But it's an almost absurdly tiny effect, something like a few nanoseconds over the course of a long flight. But crank that speed up. Push toward light speed, and the numbers become extraordinary. Imagine a spacecraft that can travel at 99% the speed of light. You board it and take a trip to a star about 10 light years away. From Earth's perspective, that journey takes about 10 years. But aboard your spacecraft, moving at that velocity, time is running at a fraction of the rate it runs for the people you left behind. The math works out to something astonishing. You might experience only about 1.4 years on that trip. While a decade ticks by on Earth, your body ages by barely more than a year. Go faster. 99.9% of light speed. The factor grows dramatically. A trip that Earthbound observers measure as taking a century might feel like only a few years to you aboard that ship. Go to 99.999% of light speed, and the contraction is staggering. Vast stretches of cosmic time collapse to the span of a human lifetime. You could, in principle, travel to the Andromeda Galaxy, 2.5 million light years away, within a single human lifetime from your own personal experience of time. You come home to find that 2.5 million years had passed on Earth. Civilizations risen and fallen, the sun aged noticeably, continents rearranged. Everyone you ever knew not just gone, but so deeply buried in the past that no record of them might remain, and you would be the same age as when you left, plus the duration of your journey. That's not science fiction. That's the physics. It's built into the mathematics of special relativity, verified in every particle accelerator on Earth, and as far as we know, absolutely true. But here's a question that trips up almost everyone who first encounters relativity. If motion is relative, if there's no absolute who is moving and who is standing still, then, from the traveling astronaut's perspective, isn't it Earth that's moving? Shouldn't Earth's clocks run slow from the spaceship's frame of reference? And yes, while they're both coasting, moving apart at constant velocity, each one does observe the other's clock ticking slower. That's a genuine feature of relativity, not a contradiction, and it sounds deeply paradoxical. This is the famous twin paradox. Here's the resolution, and it's elegant. The scenario isn't symmetric. The astronaut has to turn around to come back. That turnaround, that acceleration, that change in direction is physically real and distinguishable. The astronaut experiences forces. They change their reference frame. Earth doesn't. And when you account for that asymmetry carefully, the mathematics confirms without ambiguity. The astronaut is younger. The traveling twin returns genuinely, biologically younger than the twin who stayed home. This isn't a matter of perception or measurement error. It's a physical difference in the amount of time each person has experienced. Time elapsed differently for them. Their bodies carry the evidence. And at the heart of it is the fact that when you travel a different path through space-time, a path involving high velocities, you accumulate less time than someone who took the more sedentary path. Here's an analogy that Feynman would appreciate. Think about two roads connecting the same two cities. One road goes straight. One takes a long, winding detour. If you drive both roads at the same speed, the straight road takes less time because it covers less distance. In space-time, the geometry is reversed in a way that feels counterintuitive. Moving through space more means moving through time less. The faster you travel through space, the slower your clock ticks. A straight path through space-time, sitting still, not moving through space, actually accumulates the most time. Motion through space and motion through time trade off against each other, and light, moving through space at maximum speed, experiences literally zero time. From a photon's perspective, it is emitted and absorbed instantaneously, with no time elapse between creation and destruction, no matter how many millions of light years it traveled from our perspective. Stop. Think about that for a moment. A photon of light from a galaxy 1 billion light years away has been traveling for 1 billion years from our perspective. From its own perspective, the journey took no time at all. It was born and it was absorbed in the same instant. 1 billion years of cosmic history compressed to zero. Light doesn't age. Light doesn't experience duration. It exists, moves, and arrives, and to it, there is no between. Now we need to talk about something that may be the most unsettling implication of relativity. Something that doesn't just bend time, but demolishes one of the most fundamental assumptions in all of human experience. The assumption that events either happen at the same time or they don't. That simultaneous means something objective and universal. It doesn't. Here's the thought experiment. Imagine a train car passing through a station at high speed. At the exact moment the center of the train car passes a person standing on the platform, 2 lightning bolts strike. One hits the front of the train, one hits the back. From the platform observer's perspective, both strikes happen at the same instant, simultaneous. Measured carefully, they happen at the same time. Now consider a passenger sitting in the exact center of that moving train car. They're moving toward where the front lightning bolt struck and away from where the back one struck. Light from both bolts travels toward them at the same speed, because light always does. But since they're moving toward the front strike and away from the rear strike, the light from the front reaches them first. From the passenger's perspective, the front lightning bolt struck before the rear one. Not at the same time. Before. Now, you might think, well, they just need to correct for their motion. But that's the whole point. In relativity, there's no true frame of rest from which corrections should be made. Both frames, the platform and the train, are equally valid. Neither is wrong. The platform observer correctly reports that the strikes were simultaneous. The passenger correctly reports that they were not. Both reports are accurate descriptions of the physics of their respective reference frames. Simultaneity. The idea that 2 events happen at the same time is not absolute. It depends on the observer's state of motion. 2 events that are simultaneous in one reference frame are not simultaneous in another. The implications of this are almost too strange to process. It means that now, this moment, right now, is not a universal concept. There is no single cosmic instant that constitutes the present across the universe. A being on a planet 100 light years away, moving at a different velocity than you, would have a different now. Their present might correspond to what we consider our past, or our future. This isn't a communication delay. This isn't about not knowing what's happening there yet. This is about the structure of time itself. The universe has no universal present tense. Each observer carries their own slice of now, and these slices don't align universally. Physicists describe this using a concept called the space-time block. Imagine all of space-time laid out at once, every moment of the past, present, and future existing as a single four-dimensional structure, where any observer sees the dividing line between past and future. What they call now depends on their motion. Two observers moving differently slice that block at different angles. Their nows intersect with different events. This is what physicists mean when they say time is the fourth dimension. Not just mathematically, physically. Space and time are woven together into a single fabric, and how you move through that fabric determines how you experience each dimension. Speed through space, and you slow down in time. Sit still in space, and you travel at maximum speed through time. But here's where it gets interesting in a way that most introductory discussions of relativity miss. We've been talking about special relativity, the relativity of inertial frames, of constant velocities, of motion to flat spacetime. But Einstein wasn't done. A decade after his special relativity paper, he published something even more extraordinary, general relativity, and in it he revealed that gravity does the same thing. Mass warps spacetime. The presence of a massive object, a planet, a star, a black hole, creates a curvature in the fabric of spacetime itself. And in curved spacetime, time runs differently depending on how close you are to that mass. Deeper in a gravitational well, time runs slower. Stand on the surface of Earth and your clock ticks fractionally slower than a clock placed in orbit. Not because of motion, just because of gravity. The GPS satellites orbiting overhead experience less gravitational time dilation than clocks on the ground. Combined with the velocity-based time dilation from their orbital speed, engineers have to account for a net time discrepancy of about 38 microseconds per day. 38 microseconds doesn't sound like much, but multiply that by the speed of light. The speed at which positioning errors accumulate, and uncorrected, your GPS would drift by about 7 miles per day. The entire technology depends on Einstein being right about time. Now imagine this effect near something far more massive than Earth, near a neutron star, or near the event horizon of a black hole, where spacetime is so severely warped that time slows to a crawl compared to distant observers. Here's the thought experiment that makes this visceral. Imagine hovering just outside a black hole's event horizon, the point of no return. Your rocket engines are blasting at full power just to hold you there, not even moving inward. From your perspective, time passes normally. You feel fine. An hour goes by. But for someone watching you from far away, because you're so deep in that gravitational well, your clock appears to run almost infinitely slowly. That hour you spend hovering might correspond to thousands of years in the outside universe. And as you drift closer still, closer to the event horizon, the ratio gets worse. Near enough, an external observer would never even see you cross the horizon. From their perspective, you appear frozen in time, your image redshifted toward infrared, and then beyond detection, a ghost of your past self hanging at the edge of eternity. From your perspective, you crossed it in a moment and began your journey toward the singularity. Two descriptions, both real, both accurate, because time near a black hole has become so distorted that the connection between your now and the outside universe's now has been severed almost completely. Let's come back to something closer to home, because this brings us to perhaps the most personally significant consequence of everything we've discussed: causality. We built all of civilization on the idea that causes happen before effects. You can't be killed by a bullet before the gun is fired. You can't receive a message before it's sent. The arrow of time, past to future, cause to effect, seems inviolable. And relativity, on first inspection, seems to threaten this. If simultaneity is relative, if different observers disagree about which event came first, couldn't someone disagree about whether a cause preceded its effect? Couldn't causality itself break down? This is where physics delivers one of its most satisfying answers. No, and here's why. Causality can only be violated if information travels faster than light, because the only way a cause can appear to come after its effect, the only way the time ordering can flip, is if the two events are space-like separated, meaning no signal traveling at or below light speed could connect them. And if they're space-like separated, then neither event could have caused the other anyway. No causal relationship means no causal paradox. Nature protects causality precisely because nothing with information No particle, no signal, no influence can exceed light speed. The speed of light isn't just a cosmic speed limit for matter. It's the guardian of causality itself. It's what ensures the universe remains sensible, that causes precede effects for every observer, that time has an arrow. Remove that limit, and the entire logical structure of the universe, its ability to make sense, collapses. The speed of light is not arbitrary. It's not a coincidence. It's woven into the fabric of space-time in a way that keeps reality coherent. And this brings us to the deepest truth hiding beneath all of these extraordinary phenomena. The reason time dilation is real. The reason simultaneity is relative. The reason light speed is the cosmic constant that it is. There is no absolute external objective time ticking away in the background of the universe. Newton believed there was. He called it absolute time, a kind of universal river flowing at the same rate everywhere, independent of anything in the universe, the backdrop against which all events were measured. It felt obvious. It felt necessary. For 2 centuries of physics, it worked. It was wrong. Einstein replaced it with something stranger and richer. Time is not a background. Time is not a stage. Time is a participant. It is part of the physical fabric of the universe, a dimension of space-time, inseparable from space, responsive to matter and motion, different for different observers. There is no universal now. There is no absolute past or absolute future that all observers agree on. There is only space-time, the 4-dimensional continuum, and each observer moving through it on their own world line, accumulating their own proper time, having their own experience of temporal sequence. You are not moving through time. You are moving through space-time, and the rate at which you age, the sequence of events you experience, the span of the universe's history that corresponds to your personal lifetime. All of it is determined by the path you trace through that 4-dimensional fabric. Right now, you are sitting in what physicists call your rest frame, moving through space at essentially 0 velocity relative to the room around you. And in that state, you are moving through time at maximum rate. Your clock ticks as fast as any clock can tick. Every second of the universe's history corresponds to 1 second of yours. If you could somehow be accelerated to 90% of light speed, that ratio would shift. Your time would slow. The universe would age faster relative to you. You'd accumulate less personal time for every year that passed outside. At light speed, if you could reach it, which you can't because you have mass, your time would stop completely. You'd exist in an eternal present, frozen in time from your own perspective, the entire future of the universe rushing past you in what would feel like an instant, if you could feel anything at all. This is why mass cannot reach light speed. Not just because it takes infinite energy, but because it would require infinite time dilation, a complete cessation of experienced time. You'd have to stop experiencing the universe in order to match its speed limit. The universe, in a sense, protects the boundary between matter and light by making it physically unreachable. Here's something Feynman said that captures the spirit of all of this better than any equation could. He said that physics is not about what things are, but about what we can say about things. About the patterns and regularities we observe and the beautiful structures that underlie them. Relativity is the discovery that time is one of those structures. Not a given, not a background. A dynamic, physical, observer-dependent dimension of the universe. And the beautiful thing, the genuinely astonishing thing, is that this isn't just true at cosmic scales or extreme velocities. It's happening to you right now. Your feet, slightly closer to Earth's gravitational center, experience slightly more time dilation than your head. Your heart beats slightly slower at your feet than at your scalp, in the strictest physical sense, by an amount far too small to measure without extraordinary equipment. But it's there. The universe doesn't turn this effect on at high speeds and off at low ones. It's always operating, always. The rules of space-time apply to everything, always, without exception. You are already a relativistic being. Your experience of time is already unique to you, already different from every other person's. Not in any way you'd notice over a human lifetime, but in principle, in physics, in fundamental reality. Your path through space-time is yours alone, and the time you accumulate is specific to that path. The philosopher in Feynman always came out when he talked about these things. He didn't see deep physics as a reason for despair or confusion. He saw it as a reason for wonder, Because understanding what the universe actually is, not what we assumed it was, not what feels intuitive, but what the evidence genuinely shows, is one of the greatest things a human mind can do. Time dilation doesn't make the universe cold or mechanical. It makes it richer. It reveals that the universe has a geometry, a structure, a set of profound rules that produce extraordinary results when pushed to extremes. It reveals that our common sense intuitions, while useful for navigating daily life, are just approximations, good enough at the speeds we naturally travel, but not the deepest truth. The deepest truth is stranger. And stranger means more wondrous, not less. Somewhere in the universe right now, there are particles flying through particle accelerators at 99.9999% of light speed, living out their short lifetimes in slow motion from our perspective, surviving far longer than their rest frame lifespans would predict. Because time itself is flowing slowly for them. There are GPS satellites above your head, whose onboard clocks are carefully tuned to account for the relativistic effects of both their speed and their altitude. There are neutron stars so dense that time flows measurably slower on their surfaces than in the space surrounding them. And somewhere, perhaps, a civilization far more advanced than ours has figured out how to use these effects. How to send explorers on journeys of subjective years that span objective centuries. How to use the geometry of space-time itself as a resource. We can't do that yet, but we understand why it's possible. We know the rules. We've tested them and confirmed them and built technologies that depend on them. We know that time is relative, that simultaneity is observer-dependent, that causality is preserved by the cosmic speed limit of light, and that the universe is a four-dimensional space-time fabric where matter and motion and gravity all play roles in determining how time flows. That is not a small thing to know. That is one of the most extraordinary discoveries in the history of human thought, and it belongs to anyone willing to sit with it long enough to really feel what it means. So next time you glance at your watch, consider this. Your watch isn't measuring the universe's time. It's measuring yours, the time you've personally accumulated along your specific path through space-time. Your watch is a record of your journey through 4 dimensions. And somewhere out there, in a galaxy far enough away that light from their world is still crossing the void toward us, beings might be looking out at the cosmos and measuring their own time on their own clocks, and their now and your now are not the same now. Because the universe is not a story being told from a single perspective. It is billions upon billions of stories, each one unfolding at its own rate, along its own path, accumulating its own time. And the fact that we are conscious enough, curious enough, and mathematically sophisticated enough to know this about reality, to have figured out the actual rules of the stage on which existence plays out, that, more than anything, might be the most remarkable thing about being human. Physics isn't just a subject, it's a window. And once you look through it clearly, the universe you see is so much larger, so much stranger, and so much more beautiful than the one you grew up assuming was there. If you want to keep looking through that window, if you want to understand not just what the universe does, but why it does it, there's always more. The next question is always more interesting than the last answer. That's the thing about physics done right. It doesn't close doors, it opens them.